Great. Thank you.
Okay, you are streaming on YouTube and recording, so you're welcome to start anytime.
Okay. Thank you very much. Hello, everyone. Welcome to the session 4 of CHESS 2020. It's going to be about elliptic curve cryptography and isogenies. We will have 5 papers, and we will start now with the paper titled A Compact and Scalable Hardware Software Co-Design of SAIC. This paper was co-authored by Pedro Maat Masolino, Patrick Longa from Microsoft Research, Pedro Maat Masolino from Radboud University, Just Renz, and Leila Batina also from Radboud University. So Pedro, you can start now. You have 5 minutes plus 5 more minutes for questions. Thank you. Go ahead.
Thank you, Francisco. I'm going to start my presentation. And well, thanks for the presentation. So I don't need to start in the title or anything. So I'll just jump that part. So since I have only time to soft boil an egg, given the 5 minutes, I won't explain SAIC. So sorry, everyone. But I'll tell what the crypto system requires. So it requires quadratic extension prime field operations, such as addition, subtraction, multiplication, and inversion. And the base prime fields can go 434 up to 751 bits. And in case of before, at some point during the project, 964 was a possibility, but it's not anymore, which highlights the idea that we need to make implementations that can change with time with the parameters, because parameters change usually for new public key crypto systems. And on top of those field operations, we need Montgomery elliptic curve operations, and we also need a tree traversing procedure, and as well shake 256 from the SHA tree. And our solution is to make a CPU, and the CPU will have a software layer and a hardware layer. And the software layer will basically handle all the software parts. So basically the elliptic curves operation, the tree traversing, all those parts are done by software. The hardware layer does the prime field, which is the part that you want to optimize. Also, we have the Ketchak from the Ketchak team in order to optimize also shake. So for the results, here we can see SAIC results. The ones with the cross are only SIDH results. But what I want to highlight from our results is this. If you have your project has a constraint or a requirement that latency can be between 100 milliseconds or 200 milliseconds, then our solution is a good solution because we can achieve those timings and we are cheaper from one of the latest results from the literature. For example, for P751 parameter. The literature or one of the previous literature results will need a lot more resources, but they will achieve less timing, so around 26 to 27 milliseconds. So this is all a kind of a trade-off between what your requirements of the project and what solution fits. If the solution requires fast timing, the previous results you should apply for. If you have room for timing, then our solution is cheaper. In comparison with other public key crypto systems from the post-quantum, so both codes and lattices, SAIC needs a lot more resources, and of course, both in timing and hardware units. However, because our solution is a hardware and software co-design, we can both run everything as a software. We also have scalar multiplication for elliptic curves, for all NIST curves. So this is more of a proof of concept. So our entire hardware, without changing any VHDL, only updating the software, or even the same software can have a software of SAIC and a software of ECC. You can run both. So that's a good flexibility of the design. And between the chess publication and the ePrint publication, besides the scalar multiplications that was not on the t-chess, we also updated, there was a bug in P503 parameter, and that bug was discovered by Ultimaco because they tested our architecture. And of course, thanks for Ultimaco for discovering, and the bug is fixed, is updated, and the print has all the up-to-date results. And the code is available on my GitHub. I didn't talk in my presentation, but it is available there. And I'd like to thank everyone, and of course, thank all my co-authors. And that's it.
Thank you, Pedro, for your nice presentation. So we have time for questions. If anyone has a question for Pedro. Oh, meanwhile, I have a question for you, Pedro. You said that your design might not be the fastest one, but what about flexibility? Could you, for instance, try to implement another post-quantum scheme besides Psych?
Technically, yes, because it's like a CPU by itself, so technically can run any software. It has most of the basic instructions, and technically you could add another core processor for like the fields used in lattices or other stuff like that. I would not exactly recommend that because the CPU is not like extremely well done. So most likely what others did, like take a RISC-V already made open source core, something like this would be maybe the best option. But technically it could also work for other post-quantum schemes.
I see. Thank you. Some questions for Pedro? Some more questions? Okay, I got one more question for you, Pedro. I noticed that you are featuring Psych and also ECC, but ECC probably works in FP, in prime field, and Psych in a quadratic extension. That didn't represent any problem for you to, to manage the arithmetic? It was straightforward?
It was straightforward because technically when I did the original design, I had on my table, I think one of the most first papers on Psych where a lot of the formulas were FPM plus FP squared. So when I did the original design, I was aware that I might need the FP operations. So the FP operations are already available for the CPU, so it's easy to call them. If someone wanted to do a very different, like I would say, like if someone wanted to do a binary extension field ECC on the CPU, then it wouldn't work. Then they would need to add a coprocessor for binary extension.
I see. Okay. Well, thanks the speaker again. Congratulations, Pedro.
Thank you very much.
Okay.
Right.
So
thanks, Pedro. And then a quick reminder. So indeed, questions can be asked in the chat on Zulip, if needed, also here on Zoom. And if you, during one of the other talks, come up with a question from one of the previous sessions or previous talks, that's definitely possible. So after the last talk, we will do a Q&A for all the talks. Then the second talk in this session is actually the best paper of chess. So more info on that during the RAM session tomorrow. There will be a little celebration. For now, let me introduce the paper Minerva, the curse of ECDSA nonces, systematic analysis of lattice attacks on noisy leakage of bit lengths of ECDSA nonces. And Jan Jakar will present. So you can start sharing your screen, Jan.
Hey, can you hear me?
Yeah, not very loud.
Not very loud? Okay, I could fix that. Can you see the slides?
No.
Oh, I'm sharing the screen. I don't know.
But your screen works, but your audio is not that great.
Yeah. Okay, speak to the microphone. Is that better?
Yes, it is way better.
Okay. And I cannot share my video because I'm somehow forbidden from it. I'm not sure why. So if you want to see me, please enable my video somehow. Yes, it's saying, oh, okay, yeah, great. Yeah, thank you. Right, so this is our work on titled Minerva, the curse of ECDSA nonces. It presents a group of vulnerabilities in ECDSA signing, a group of side channel vulnerabilities. And this is joint work with many people from the Center for Research on Cryptography and Security at Maastricht University. So the story begins with the EC Tester tool, which is a tool for testing black box ECC implementations that we developed. It targets Java cards and software libraries, and it has many kind of test suites that you can imagine. And by the end of implementing all those test suites, we also thought of testing timing. So we tested timing of ECDH and ECDSA. I will stop here and shortly introduce ECDSA. So in ECDSA signing, the signer first generates some random nonce, then the scalar multiplication with the random nonce and the generator, and then some modular arithmetic with the private key, these values, and finally outputs the signature, right? So what we expected when we looked at timing is something like this. So you can see a heat map of the most significant byte of the random nonce, and this is the duration of signing. This is a nice constant time implementation. It's pretty much a flat line, nothing to see here. Instead, what we got was this for the Athena ID Protect smart card, which is FIPS validated and common criteria certified smart card. Then we got this for the default implementation in Java on binary field curves. We got this in libgcrypt, matrix SSL, crypto++, and finally even Wolf SSL if you look really closely. So what's going on? Why are we seeing these weird shapes? It's basically the scalar multiplication leaking the bit length. In this kind of linear way that the loop in the scalar multiplication is somehow directly or indirectly bounded by the bit length. And you might now be asking, okay, Jan, but how do you exploit this? It's just a few bits, a few leading 0 bits of some random value, random nonce. But it's well known that this kind of knowledge of some information about the random nonce of many signatures can be turned into the hidden number problem, and which can be solved using lattice reduction techniques and using problems like CVP or SVP, and you can get the private key out of that. So how this works is that you collect n signatures for some large amount of signatures, take d of the fastest. These fastest signatures have somehow the most amount of leading 0 bits, so the most amount of information, so you want to use those. Then you assume some bounds on those, kind of how many leading 0 bits are there. You form some inequalities stating this fact that there are some leading 0 bits. Then you construct this hidden number problem lattice and target vector, basically solve either the closest vector problem or the shortest vector problem, and then you magically get the key out of it at the end. So this is quite nice, but contains many questions of, okay, how do you assume those bounds? Do you do CVP or SVP and stuff like that? Do you do recentering, which is also a possibility? Do you do nonce differences, which you can do here? Do you do random subsets to fix some errors, or do you do what we introduced and call U-bit flips? So we were in a good position to analyze this. We collected 4 data sets of signatures with varying noise from the vulnerable implementations. And to analyze this properly for all the parameters and so on, we decided to run the attack 5 times for a grid of 2 parameters, basically the number of signatures collected, so the number of signatures the attacker collects from the implementation, and the number of signatures that's actually used, so the D fastest signatures. And then we are able to kind of plot these 2D heat maps of success rate of how the attack behaves when the attacker gains more and more signatures, and what are the optimal values of those 2 parameters. So we evaluated many kind of techniques and attack improvements. Here you can see the basic inequality that you start with. And so how do you assume those bounds? In most previous works, this was somehow constant or sometimes computed based on some other side channel. But in our case, we achieved a much better success rate by better estimating the true distribution of the leading 0 bits of these first signatures, which is somehow geometric or geometric looking, which increase the success rate so that the attack starts working like thousands of signatures less. You need thousands of signatures less than if you just use constant bounds. We also compared CVP and SVP, and we found that we confirmed what other works said, that SVP works better and that you perhaps should use it, that it improves success rate. We tested recentering, which allows you to kind of gain 1 additional bit by shifting the nonces in some way, and we again confirmed the previous works that this really does works and helps your success rate. We tested the random subsets method, which was a previous work on how to fix errors for these kind of lattice attacks, which takes the random D signatures out of the 1.5 D fastest, does this a many amount of times and hopes that it takes a random subset that doesn't have errors. And we found that for a noisy data set, it does improve success rate, but for a data set that's not noisy, it decreases the success rate because you are not taking the best of these signatures, the signatures with the largest amount of information. We also tested nonce differences, which is just something that you can do. We didn't really think it would improve anything, but we found out that it somehow fixes errors sometimes, and we found that it increased the success rate similarly to how recentering does. And lastly, our new technique allows us to not do the costly step of lattice reduction for basically for any guess. So it allows us to somehow brute force fixing some errors in those nonces. So if it happens that our inequality does not hold for some reason, so we misjudged and we set our bound kind of too high, and there is some bit set in the nonce that we did not expect, we can kind of brute force these bits, and we don't have to reduce the lattice, which is the costly step of this attack, many times. We do it just once and then kind of brute force only the cheaper part of the algorithm. So to conclude, we got private key extraction in ECDSA on a certified smart card and some libraries. We introduced 2 new methods for these kind of lattice attacks based on geometric bounds and these U-bit flips. Using the data that we gathered, we performed systematic analysis of lattice attacks on bit length leakage, and we improved the success rate of the attack such that for data from the TPMFL paper, we were able to succeed in the attack with only 900 signatures instead of 40,000 as was claimed in that paper. Thanks, that's it.
Thanks a lot, Jan. If there are any questions. Yes, so there's a question from Mehdi. So he asked, can you expand on the CVP versus SVP issue? In the paper, I think you mentioned that SVP is better for single instances, but CVP lets you try several instances by reducing the hidden number problem lattice first, except with the inferior quality compared to the shortest vector problem.
Yeah, exactly. So we are using only here. What we mean by CVP is that we are solving CVP via Babai's nearest plane algorithm, which I mean isn't the best way to solve CVP, but it's a very cheap way to solve CVP. So yeah, we are really an SVP. We are solving again by reducing the lattice and then just looking at the basis vectors, right? So we are using very, I would say, primitive ways of solving these 2 problems and comparing really only those. Yeah, so there is the trade-off. If you use SVP, you kind of embed the information about these U values here into the lattice. So you, after you reduce it, you cannot change them anymore. So if you want to change them, which allows you to fix some errors, you have to use CVP, and then these UIs are only in the target vector. So brute forcing and changing or fixing these errors only amounts to kind of, yes, you have your fixed lattice, and you are only looking at the different points of it, or trying to find the closest vector to different points around it. So yeah, I mean on the heat maps you can see that that SVP and this kind of U-bit flips technique are very comparable, I would say. Yeah.
All right, thanks. So there's another question from Benedict. So he says, nice work. Thanks for the great talk. So it seems that your initial attack works with around 5,000 signatures. Isn't that dangerously close enough that it's a threat to the real world applications? How long does it actually take to obtain one of these signatures?
Yeah, I mean, yeah, even the actual attack is very practical. Well, okay, it depends on the smart card, which is really, really slow. Collecting 5,000 signatures, I don't want to say exactly how long that will take, but it might be hours, possibly. I don't know. But with all the communication and the setup and whatever, yeah, but the attack itself, then when you have the signatures, is very fast. So the attack, in any case, in any of these techniques, perhaps with the exception of the random subsets one, should be in just like 5 minutes. So after you collect your signatures in 5 minutes, and you have the private key, basically.
Okay, and then yeah, also maybe one question from me. So also, yeah, really nice work. So this is about ECDSA nonces. So what about deterministic signature schemes?
Mm-hmm. Yeah, so when you use deterministic nonces, it doesn't really help you. I think it can actually hurt you because noise in this case is a problem for the attacker, right? But when deterministic nonces are used, what the attacker can do is send the same or like query the same message many times and then obtain the timing samples for that, kind of average them, and that gives a much better like much better information about the number of leading 0 bits, right? So actually using deterministic nonces here can hurt you because it can be abused to gain better information. And if you have better information and less noise on the amount of leading 0 bits, you can abuse it more, and you can abuse it with less signatures essentially, or you can, yeah, you can succeed where the attack with deterministic nonces wouldn't.
All right, thanks a lot. If there are more questions, let's keep them for after the final talk in this session. Thanks.
Thank you. Bye.
Okay, thank you very much. So we are moving to the third paper in this session. It's going to be a paper titled "When One Vulnerable Primitive Turns Viral: Novel Single Trace Attacks on ECDSA and RSA." It will be presented by Alejandro Cabrera Aldaya, and is a work co-authored by Billy Bob Bromley, from both of them from Tampere University in Finland. So Alejandro, please go ahead.
Thank you so much for the presentation. Okay. Well, this is a short talk about novel single trace attack on ECDSA and RSA paper. Binary GCD-based algorithms have many uses in crypto. For instance, RSA and ECDSA, these are some examples for them. These primitives can be used for either computing the GCD or for computing modular inverses. MBDLS model inversion implementation follow these steps. It is very interesting that before actually computing the modular inverse, the GCD of the input are computed. Therefore, such an analysis on the binary GCD primitive can be reused for all GCD inversion use cases in this library. The binary GCD implementation in MBDLS is very similar to the classic binary GCD algorithm and have an iterative structure with several conditional operations. The attacker's goal is to retrieve information of these operations. Some leakage models have been proposed to analyze how the control flow leakage relate to algorithm inputs. In 2007, the all or nothing model was proposed that required the knowledge of all the control flow information to recover all bits. 10 years later, a partial model was proposed that offered more flexibility. It's allowed to recover partial information for partial leakage of the execution flow. The partial model has some advantage over the previous model. As part of this research, we developed two end-to-end attacks on MBDLS running inside Intel XGX enclave. The side channel signal we use as attack, interroot-driven attack using XGX step framework. This attack allows to count the number of executing instructions inside a memory page. This signal could be noisy, and after some tweaks in our procedure, we can change the noise by percentage. The initial experiment suggests an expected high success rate. So the first attack is against ECDSA, especially in the linear part, where the nonce K is inverted modulo P. There is very well-known countermeasure that masks these nonce using a multiplicative masking. On paper, this countermeasure looks like this. However, the implementation always has the final word, and MBDLS, instead of multiply on modulo P is multiplied on the integer realm. Therefore, when the product A equal MK, is no longer safe. When it is inverted, well, in the MBTLS modular inversion primitive, especially when the binary GCD primitive is called, a side channel attacker could recover that information on K from the product. One permutation of the factor of MK will lead to K, and the number of permutations is small with very high probability according to the number theory results. After developing all the tooling for the attack, we repeated a single trace around 1,000 trials and obtaining 99% success rate. The attack time has a median of 15 minutes per trial. The other attack, a target RSA, in this library, when a private key is loaded, the CRT parameter, the inverse of Q modulo P, is computed. This computation uses the same binary GCD primitive. In this use case, both inputs are secrets. Regarding this, it was analyzed using the all or nothing model back in 2007. However, no information and publication have been done regarding the partial model. For this attack, we also repeated the attack 100 times, obtaining a similar success rate, 99%. And we see how, in this table, we compare the different models with the number of candidates that we have to test until solution. And we see how the partial model requires less candidates than the all or nothing one. Of course, these numbers are inside practical domain for testing all of them, but the partial model have more impact where a noisier side channel is used. After finalizing this work, well, one of the conclusions is the countermeasure implementation must strictly follow math description, because a wrongly implemented countermeasure offers a false state of security. Regarding the partial model on binary GCD algorithms, we show that it can be used when both inputs are unknown. At the same time, it reduces the uncertainty and noise influence. Thank you very much.
Thank you, Alejandro, for the nice presentation. So we have questions for one or two questions. Do you have questions for Alejandro? Yeah, I don't see any questions. So I have one question for you, Alejandro. As a countermeasure, you are mentioning the masking countermeasure in GCD. How would you compare against constant time implementation of GCD? Which one would be better according to your experience, masking or trying to have a constant time implementation of GCD?
Okay, I think that if randomness is free, masking is a good one, because constant time implementation could have issues. It depends on the side channel signal employed, but it could be possible to break constant time binary GCD algorithm, and that could be not possible to break in the other direction. And it's actually easier to implement a countermeasure based on masking than a constant time one, in my opinion.
Francisco, you're on mute.
Thank you, Jope. Sorry. Any other question for Alejandro? If not, then thank you very much to the speaker again. And then we move to the fourth paper of this session, which is going to be, so we start again because it's the same speaker. So it's from A to Z, projective coordinates leakage in the wild. This is a project by Alejandro Cabrera Altaya, Cesar Pereira Garcia, and Billy Bob Bromley from Tampere University in Finland. So once again, Alejandro, please start your second presentation in this session. Thanks.
Okay, thank you for the presentation. This is a short talk for the projected coordinates leakage in the white paper. Regarding scalar multiplication, the representation of elliptic coup points matter for performance. Affine coordinates require costly inversion, as therefore projected coordinates are preferred because they trade some inversion for multiplication and only require one inversion at the end. Usually the representation of the internal representation to the scalar multiplication is not public. However, a channel adversary could retrieve it, for instance, using a channel attack to the modular inverse during the modular inversion of C modulo P. However, is the projected representation of the point secret? This question was already answered by Nakachera et al., demonstrating that point representation also matters for security. This attack, using this attack, could be possible to recover some bit of the scalar. So it can be used to break ECDSA. In a nutshell, the projected coordinates attack is as follows. Let's start with the double and algorithm, and let's assume that the attacker knows the projected representation of R. Starting from this information, the attacker guesses that the last processed bit was an A1. So we have to reverse the addition operation and a double. This operation requires computing modular roots. Sometimes they exist, sometimes they don't. Then if guessing the last processed bit was a 0, in this case, you only have to reverse a double operation. So let's assume that in this case, there is no solution. So the attacker learned that the last processed bit of the scalar was indeed a 1. Repeating this process for several iterations could be possible to recover some bit of the scalar. The success rate of this attack depends on several factors. Here are listed some of them, and inside each category there are many options. Additionally, the attack can be adapted. Regarding attack adaptability examples, the Montgomery ladder was considered safe in previous work. Also, a countermeasure that based on randomizing the generator for doubling and scalar multiplication was proposed to mitigate this attack. As part of this research, we demonstrated that they don't prevent the attack because they could be possible to recover the number of trailing zeros of the scalar. Regarding analysis of how open source libraries could be affected by this attack, specifically to a side channel attack to the binary inversion function, we analyzed 12 libraries and only four of them we categorized as not threatened by this attack. Additionally, we implemented end-to-end attack on one of these libraries to target ECDSA. The candidate conversion was performed using BEA, and the side channel signal was a faithful attack on Intel SGS enclave that allows to track the sequence of executed memory pages. The traces are available online. The attack roadmap is the following. Okay, you capture some ECDSA traces specifically during the inversion of C, and from there compute the projected representation of the coup point. After that, you point that to the projected attack algorithm, and hopefully for an attacker, he can recover some bit of the scalar. Repeating this process several times could be possible to recover the private key using a hidden number problem solver. The results after extensive testing, it was possible to recover the private key with 100% success rate on 50 triggers using only 2,000 traces. The conclusion of this work is a projected coordinate leakage has received little attention in academy and industry. The success rate depends on several factors, therefore secure by default mitigation are preferred. The Montgomery ladder does not protect as believed before, neither the randomizing the generator in the dollar adapt algorithm prevent the attack. We recommend, as part of this research, randomizing the projected representation of the output point because it should prevent both side-channel attack and for injection attacks. Thank you very much.
Okay, thank you very much, Alejandro, for your presentation. So we have room for questions. Any questions? Okay. So I have one question for you, Alejandro. Okay, go ahead.
Oh, are there any fields for which this technique is particularly powerful? You mentioned that it depends on the characteristic of the finite field. Are there fields where you can recover many more bits than in other ones?
Yes, actually, for instance, regarding the NIST corps, the P224, 2224 is more susceptible to the attack than the P266. It depends, but it not only depends of the characteristic of the final field, because it depends on the scalar multiplication algorithm that define also on the lead curve form and the projected representation, because all these elements defines the equation that you have to reverse that define the modular root that you have to compute. So, and the behavior of these modular roots is what depends on the characteristic of the field. So it's not the same, maybe a cubic root on some field and that a fourth root in another field. And in general, what we see in our experiments, also in the original paper, that is that the tree grows very quickly. So often in practice, it seems difficult that you can recover many bits. So for protocols like ECDSA, you can manage. I mean, an attacker can manage to recover a secret, but I don't think that other protocols. Well, it depends on the protocols.
Thanks.
Okay, some more questions for Alejandro. Just a quick question, Alejandro. Have you tried this attack to isogeny-based protocols where also Montgomery ladders are used?
Sorry?
Yeah, in the case of isogeny-based protocols for quantum cryptography, have you tried this attack because they use also Montgomery ladders?
No, I haven't tried this attack on PQC implementations, but it could be tested. It could be tested, but I don't know if those protocols are susceptible to partial leakage, so it depends on that.
Okay, thank you very much.
Thank you.
So thank you. We move then to the fifth paper of this session. Please, Joppe.
Yeah, thanks, Francisco. Yeah, so after 3 more attack-related papers, we now turn to a more constructive one. So I'm glad, to introduce faster Montgomery and double add letters for short Weierstrass curves, a presentation and paper by Mike Hamburg. Mike, the floor is yours.
Hi all. So this is a paper on how to speed up elliptic curve scalar multiplication on short Weierstrass curves. So that would be like the NIST or the brain pool curves. And it's a Montgomery ladder or a Joie ladder. So you're given only the scalar and the point that you want to multiply, not any table of pre-computed multiples of P or anything like that. And then it's a regular algorithm, so it's good for side channel resistance. And we can do either X only or XY. In some cases, XY is slightly more expensive. So the algorithms that this is based on are the 3-point variant of the Joao or Montgomery ladder, where you set up the ladder state according to the base point, and then at every step, so you scan through the scalar bits from either left to right for the Montgomery ladder or right to left for the double add or Joao ladder. And then at every step, you conditionally swap 2 of the points and then apply this ladder step, which in all cases, it's given a state of 3 points where one of them is the sum of the other 2. And then you need to update the state so that one of the points is the same. One of them is doubled and added to the third. The representations of the points in the state, you could use some weird representation of these 3 points. It doesn't have to just store the X and Y coordinates of each one, but you do need to be able to swap them. So the representations of Q and R have to be the same for the Montgomery ladder, and P and Q have to be the same for the Joao ladder. There's been a lot of previous work in this area. It's well known that this is fast on Montgomery curves, but it's slowly been improving over the past decade or two for short Weierstrass curves. In this talk, it gets down to 11 multiplies per ladder step. So the formulas are based loosely on the Kim et al. Papers from 2017, which I sort of distilled into a faster and simpler form for the CHES 2017 rump session. And so the main insights over previous work are that these 3 points P, Q, and R, or their negations, lie on a line because they satisfy, P plus Q equals R or something like that. And so the slope of this line could be stored as part of the ladder state, and that's very useful information. The other insight, which is also an improvement over the CHES rump session from 2017 even, is that you don't actually need to compute the X coordinates of P, Q, and R, because what you really need in the formulas are the differences between them, which is sort of only 2 dimensions of information rather than 3. So you end up being able to do like less work by computing fewer of them. So you end up with a ladder state as shown at the bottom here, which is, it's kind of probably minimal. It's only got 4 coordinates actually. So it's a cozy ladder state, and you store difference of X times Z squared for the 2 pairs of points, Q minus P and R minus P. And then you also store YZ cubed, and then the slope of this line times Z. You don't store Z itself, like is common with certain cozy formulas. This is just for one of the versions of the ladder. The other ones have sort of similar states, maybe with 1 more coordinate. So the new ladders, there's the one that I mentioned, this sort of simpler version that's most closely based on the 2017 work. This one has the best side channel properties because it doesn't reuse the output of a ladder step within the ladder step itself, which deters collision attacks. There's a parallel ladder that's, you could make it as fast, but the actually parallel version is slightly more operations, but they parallelize 4 ways, which makes it probably actually as fast as, the latest work by Hissil et al. Or whoever on the Montgomery ladder on Montgomery curves. So you have only 3 multiplies and 3 adds, but in parallel. And then there's a Joao ladder, which is a little bit slower, but it requires less memory than any scalar multiplication implementation that I've seen before. Only sort of 5 field registers plus like the scalar and curve constants. There's also some trick around setting up the ladder. So if you have X and Y, this is easy, but if you only have X, then how do you compute like YZ cubed and MZ for the ladder state, because you don't have Y, but you do have Y squared because it's a function of X. So if you said Z equals Y, even though you don't know either Z or Y, then you can compute ZY cubed because it's a function of Y squared. There are also 3 ways to finalize the ladder state. And this is like slightly tricky, right? Because you want to divide by Z, but you don't have Z. It's not stored in the ladder state. So you have to solve for Z. So depending on what curve you're using, mostly this middle one, which uses the curve equation, is the best way to do it. And finally, there's some discussion in the paper on completeness. So like many elliptic curve scalar multiplication algorithms, this is not complete. It fails precisely in the case where the point at infinity appears in the latter state, and it kind of has to because it's cos-z. So z equals 0 screws you. But there's a new result that if you have sort of any 3-point ladder at the cost of some messy state machine, you can dodge the point at infinity by sort of like taking a different path that goes around it. So the details of that are in the paper, or rather in the supplemental material. So that's all.
Thanks a lot, Mike. Great talk. So are there any questions? Otherwise, let me kick off with one question. You already alluded and mentioned to this is likely to be minimal. Is there, do you have any feeling? Can we expect more progress here related to faster Montgomery ladders for Weierstrass curves?
You may be able to make it faster. I think it's less likely that you can make the state much smaller than 4 coordinates because it kind of encodes 3-ish dimensions of information plus z. So it should be, or two dimensions because there's a constraint, but the curve may have more than q points. I mean, more than the field characteristic points on it. So it seems unlikely that you can get down to 3 coordinates in the latter state only. But you might be able to do it faster.
And what is your feeling? Will this ever be close to what you can do on a Montgomery curve?
I don't know. Yeah, I mean, I didn't expect this improvement, but I wouldn't be shocked if there was another one.
Okay, then there's a question from Benedict in the chat. So he asks, so doesn't the conditional swap open up a side channel vulnerability?
Well, yeah, I mean, in the end, you can't do the same sequence of steps on the same data without swapping anything, independent of K, because otherwise you don't use K. Conditional swaps, or, more likely conditional swaps of pointers, seem to be the best thing that we have so far for dealing with that. You can add additional countermeasures against sort of power analysis, but that gives you at least constant time. But yeah, I mean, it's not, it doesn't make it trivial to protect against hardware side channel attacks. You still have to do work there.
Okay, and then there was another question. In the full talk, the optimization of the formulas seemed at times like something that could be automated, or at least somehow searched through the possible changes to the formulas. Do you think this is something that is doable?
Yes. I guess when I set out to do this, I was actually setting out to write a paper about how the chess 2017 thing worked, because I thought that eventually it should get written up. And then I accidentally found the better formulas. And if I had known how long I was going to be fiddling with formulas by hand, then I would have tried to automate it at the beginning. But I didn't. So yeah, go ahead and automate the search. You might find something faster.
Cool, thanks.
All right, thanks a lot. So maybe if there are any other questions, either for Mike or for any of the other speakers, this is the time to either post them. So there's a question from Francisco. Do you have any clock cycle timings of your Montgomery ladder?
No, no. We've got implementations in proprietary hardware, but I didn't, re-implement OpenSSL or anything. So it's like 8% faster than the previous one, which is about what you'd expect, because it goes from 12 down to 11 multiplies.
Okay, thank you very much. Some more questions for the speakers that you may have?
If not, then yeah, let's thank the speakers for the great talks and for all the questions. Thanks, guys. And then we now have a social break, and then we continue with session 5 on theory and evaluation of side channels.
before we go to the break, thank you very much for organizing